It's November 2025. Astronomers aim their telescopes at an interstellar visitor called 3I-ATLAS, expecting to see what comets have shown us for centuries, a tail streaming away from the sun. Instead, they find something that shouldn't exist, a glowing filament pointing directly at the sun, not away from it, toward it. Harvard physicist Avi Loeb looks at the data and proposes something that makes his colleagues deeply uncomfortable. This might not be a single object at all, but a swarm, trillions of fragments trailing behind an accelerating core. The math checks out. The physics doesn't. Stay with me, because what we're about to explore might rewrite everything we thought we knew about what's drifting through our solar system. And the implications are genuinely unsettling. If you're as captivated by this as I am, go ahead and hit that like button and subscribe so you catch every new development as it happens. Leave a comment telling me your location, your local time, and your honest take on whether we're being told everything about these discoveries that could reshape our understanding of reality. Part 1. The anti-tail nobody expected. It's November 2025. Astronomers point telescopes at 3I-ATLAS, and what they see defies decades of comet lore. The images that come back are not just unusual, they're wrong. Fundamentally, physically wrong, according to everything we've been taught about how comets behave. Picture this, a teardrop-shaped coma, glowing softly in the darkness of space, roughly 270 million kilometers from the sun. But extending from that coma is something that shouldn't exist. A filament, a ghostly extension reaching outward, and it's pointing directly at the sun. Let me be clear about why this matters. Every comet you've ever seen in a textbook, every diagram, every childhood astronomy book shows the same thing. Tails point away from the sun. Always. This isn't a suggestion. It's physics. Solar radiation pressure and the solar wind push dust and gas away from a comet's nucleus, creating those magnificent tails that stretch millions of kilometers into space, always fleeing the sun's fury. It's as reliable as gravity itself. Except 3I-ATLAS apparently didn't read the textbook. Avi Loeb and his team released stacked ground-based images showing what they're calling an anti-tail. The morphology is unmistakable. There's the coma, yes, but this sunward filament is stable, persistent, and pointing in precisely the wrong direction. At this distance from the sun, solar radiation should be pushing material outward with tremendous force. The pressure might be weaker than at perihelion, sure, but the direction is non-negotiable. Dust gets pushed away, gas gets ionized and swept back. That's the rule. So if this isn't following the rule, what exactly are we looking at? The standard models fail here, and they fail spectacularly. Radiation pressure at 270 million kilometers is still significant enough to dominate the motion of small particles. Any dust grain small enough to scatter visible light should be blown away from the sun, not toward it. The solar wind, that constant stream of charged particles flowing outward from our star, should be doing the same thing. There's no conventional mechanism in our current understanding of cometary physics that produces a stable, sunward-pointing structure. Unless, of course, this isn't a tail at all. That's the question that should be keeping astronomers awake at night. If it's not a tail in the traditional sense, if it's not dust being pushed by radiation pressure, if it's not gas being ionized and swept away, then what physical process could possibly create this geometry? What are we actually seeing? Maybe it's dust, but not the kind we're used to. Maybe it's gas that's behaving in ways our models don't predict. Maybe it's something we don't have a classification for yet, something that doesn't fit neatly into our comet taxonomy. Or maybe, and this is where things get uncomfortable for a lot of scientists, maybe 3I-ATLAS has a fundamentally different structure than we've assumed. The tension here isn't just about one weird observation, it's about what this geometry implies. If 3I-ATLAS can produce a stable sunward glow, it suggests this object might not be a simple chunk of ice and rock tumbling through space. It might have internal structure, composition, or dynamics that we haven't encountered before. It might be hiding something. Could this be evidence of a swarm? Multiple objects moving together, creating collective optical effects that mimic but aren't actually a comet tail? Could this be a sign of behaviour that's not entirely passive, not entirely at the mercy of solar forces? Could our models of interstellar objects be missing an entire class of things that simply don't behave like solar system natives? Here's what makes this so unsettling. We've been studying comets for centuries. We've observed thousands of them. We've sent spacecraft to rendezvous with them, landed probes on them, analysed their composition, tracked their orbits with extraordinary precision. We thought we understood them. The physics seemed settled. Solar radiation pushes small particles. That's it. That's the model. And then 3I-ATLAS shows up and points a glowing finger directly at the sun, as if to say, your model is incomplete. Look at it this way. Imagine you've been teaching children that water always flows downhill. It's a simple, reliable rule. Gravity pulls water down, always. And then one day, someone shows you a stream flowing uphill. Not a little trickle being pushed by wind. A stable, persistent flow, defying gravity for no apparent reason. Your first instinct is to doubt the observation. Maybe it's an optical illusion. Maybe the camera angle is misleading. But then more images come in, more data, and the stream is definitely, unambiguously flowing uphill. That's where we are with 3I-ATLAS right now. The sunward filament isn't a fleeting thing. It's not a momentary quirk of illumination or a data artifact from a single telescope. Multiple observations, stacked images, careful photometry all confirm it. Something about this object is producing a stable glow in a direction that violates our expectations so thoroughly that we're forced to question not just this one comet, but potentially our entire framework for understanding these objects. And here's the kicker. This isn't even the strangest thing about 3I-ATLAS. The anti-tail is just the visible symptom, the thing that caught everyone's attention. But underneath this geometrical puzzle lies something even more troubling. Something that shows up in the orbital data, in the residuals, in the careful mathematical models of how this object moves through space. Because what scientists found next made the anti-tail look like the least of its problems. Part 2, the delta problem, a non-gravitational acceleration that behaves too cleanly. Let's talk about how things move in space, or rather how they're supposed to move. In an ideal universe, the orbit of a comet is purely gravitational. The sun pulls it, the planets tug it slightly, and you can predict its position centuries into the future with nothing more than Newton's laws. But real comets are messy. They're not solid billiard balls. They're volatile, active, leaking gas and dust as they warm up. That outgassing creates jets, little rocket engines firing in random directions, pushing the nucleus this way and that. It's chaotic. It's unpredictable. It's what makes comet orbit determination such a headache. Astronomers call these deviations non-gravitational accelerations. They're the fidget factor in comet motion. And here's the thing. They're supposed to be messy. Jets fire asymmetrically because comet nuclei rotate, because different areas have different compositions, because sublimation depends on sunlight angle and surface features. The resulting acceleration changes in magnitude and direction as the comet tumbles and rotates. It's sporadic. It's noisy. 3I-ATLAS doesn't do that. Post-perihelion orbital fits show something deeply strange. A persistent radial outward acceleration away from the Sun. The coefficient, called A1 in the technical literature, was initially measured near 1.6 times 10 to the negative sixth astronomical units per day squared, normalized to 1 AU. Later, as more data came in and fits were refined, that value dropped to around 4 times 10 to the negative seventh. The magnitude changed, sure, but the character of the acceleration remained eerily consistent. And here's what makes orbital dynamicists uncomfortable. This acceleration scales roughly as 1 over r squared with heliocentric distance, exactly like solar gravity, exactly like a force that depends on the inverse square of distance from the Sun. That should not happen with comet outgassing. Think about it. Comet jets are like tiny, randomly firing thrusters. Sometimes they push forward, sometimes sideways, sometimes the nucleus rotates and the jet points in a completely different direction. The net effect over time might produce some average acceleration, but it should be jittery, variable, dependent on rotation state and illumination geometry. It should not produce a smooth, predictable inverse square law force that persists for months as the comet travels millions of kilometers through space. Let me give you an analogy. Imagine you're watching 2 boats on a river. One is being jostled by random currents, eddies, waves, and wind gusts. It drifts erratically, sometimes faster, sometimes slower, its direction constantly shifting. The other boat moves with smooth, steady progress, as if pushed by an invisible, perfectly even wind that somehow maintains constant pressure regardless of the boat's position. Which one seems natural? Which one makes you suspicious? 3I-ATLAS is the second boat. The magnitude of the acceleration isn't the problem. Plenty of comets show non-gravitational forces of similar size. What's strange is the consistency. The fact that it persists. The fact that it seems to follow a mathematical law rather than the chaotic behaviour we expect from sublimating ice. As 3I-ATLAS moves away from the Sun, as the solar flux decreases, as the temperature drops, the acceleration continues to behave predictably, scaling with distance in a way that feels less like geology and more like engineering. Some scientists argue this could still be natural. If the outgassing is isotropic, meaning it happens equally in all directions, you might get a net radial force. Or if the nucleus has a very specific shape and rotation that creates symmetric sublimation patterns, maybe you could reproduce this effect. But achieving that kind of symmetry is extraordinarily difficult. Comet nuclei aren't spheres. They're irregular potato-shaped chunks with varied surface composition. Getting uniform sublimation as the illumination angle changes, as the object rotates, as different volatiles activate at different temperatures, that's asking a lot from nature. And yet, a recent peer-reviewed preprint offers exactly that explanation. A team of researchers developed a thermophysical outgassing model using a mixture of carbon monoxide and carbon dioxide ices. They claim that under realistic surface conditions, with a nucleus radius somewhere between 0.5 kilometre and 3 kilometres, you can reproduce the observed non-gravitational acceleration. The model works, mathematically. It fits the data. So problem solved, right? Natural outgassing, case closed? Not quite. Because here's where the scientific community splits into two camps. The first camp, we'll call them the naturalists, looks at that thermophysical model and says, see, there's your explanation. Complex, but plausible. No need for exotic physics. 3I-ATLAS is just a weird comet with unusual but not impossible properties. The second camp, let's call them the skeptics, looks at the same model and says, you're asking us to believe that this object's composition, structure, rotation and volatile distribution all conspire to produce acceleration that mimics a simple mathematical law. That feels suspiciously like fine-tuning. That feels like we're forcing the data to fit a preconception rather than following where the data leads. And that brings us to the uncomfortable question. If this isn't straightforward outgassing, if the naturalist explanation requires increasingly specific and unlikely assumptions, then what else could be producing this acceleration? What mechanism, natural or otherwise, creates a smooth, persistent, inverse square law force that acts on an object as it crosses the solar system? The next segment explores the most provocative answer anyone has dared to propose publicly. Part 3. The Swarm Hypothesis. Why Loeb said the quiet part out loud. Avi Loeb has a reputation. He's the astronomer who suggested Oumuamua might be artificial. He's the physicist who doesn't shy away from uncomfortable hypotheses. And when he looked at 3I-ATLAS, he saw something that made him put forward an idea that most of his colleagues probably wish he'd kept to himself. What if 3I-ATLAS isn't a single object? What if it's a system? Here's the hypothesis. 3I-ATLAS consists of a nucleus, probably small, probably experiencing some kind of acceleration followed by a trail of fragments or debris. These fragments aren't active, they're not sublimating, they're inert, maybe rocky, maybe metallic, just passive chunks trailing behind. And the separation between the accelerating nucleus and this passive swarm creates the geometry we're seeing, the anti-tail. Let me walk you through the math, because the math is what makes this hypothesis so unsettling. We'll use delta to represent the acceleration fraction, the ratio of non-gravitational acceleration to solar gravity. Based on the observations, delta is roughly 0.0002. The current heliocentric distance of 3I-ATLAS is approximately 270 million kilometres. If the nucleus is being accelerated but the fragments aren't, the relative displacement between them grows over time. That displacement is delta times r, which gives you roughly 54,000 kilometres. 54,000 kilometres. That's the predicted separation between a pushed nucleus and passive debris at this distance. Now convert that to angular size as seen from Earth. At the distance of 3I-ATLAS, 54,000 kilometres corresponds to an angular separation of about 0.7 arcminutes, and guess what? That's roughly the observed length of the anti-tail. The geometry matches, perfectly, disturbingly. Let me give you a visual. Imagine a car driving down a highway, towing a long trailer filled with dust. Now imagine the car suddenly gets a small but steady boost, a hidden engine that pushes it slightly faster than it should be going. The trailer being passive doesn't get that boost. Over time, the car pulls ahead. From far away, watching this happen, you'd see the car leading and the dust trailer lagging behind. The separation grows proportional to distance travelled. That's the swarm hypothesis in a nutshell. Except instead of a car and trailer, you have a comet nucleus and a cloud of fragments. And instead of watching from the roadside, you're observing from Earth, seeing the nucleus pulling ahead while the swarm lags, creating an apparent extension that points back toward the sun because the fragments haven't caught up yet. But here's where it gets tricky. For this to work, the fragments have to be non-evaporating. They can't be ice because ice sublimates, produces outgassing, and would also experience radiation pressure and recoil forces. They'd accelerate too, just like the nucleus. For the swarm to stay separate, for it to lag behind while the nucleus pulls ahead, the debris has to be inert, rocky, metallic. Stuff that doesn't sublime, doesn't outgas, doesn't respond to solar heating except by absorbing and re-radiating thermal energy. What kind of comet has a trail of inert, non-volatile debris? This is where the swarm hypothesis starts to make people uncomfortable, because if such a debris field exists, it provides something incredibly useful. Surface area. Lots of it. Far more than a small nucleus could provide alone, and surface area means reflected sunlight. It means brightness. It means you can have an object that looks surprisingly luminous without requiring massive amounts of mass. Think about it this way. A single rock in sunlight reflects a certain amount of light based on its size and reflectivity, but a million tiny fragments spread out over thousands of kilometres collectively have far more surface area than that single rock. They scatter sunlight more efficiently per unit mass. If you wanted to create something bright without making it massive, fragmenting it into a swarm is a remarkably effective strategy. And this leads directly into the next mystery. 3I-ATLAS's brightness doesn't match expectations for a small, solid nucleus. The coma, the halo around it, seems to contribute most of the visible light, which is weird if all you have is a single chunk of rock or ice. But if you have a swarm, if you have countless fragments scattering sunlight, suddenly the photometry starts making more sense. Of course, there are objections, plenty of them. Comet scientists will point out that keeping a debris swarm coherent over months or years is difficult. Solar radiation pressure should blow small fragments apart. The solar wind should erode them. Random collisions should cause dispersion. Why would a swarm stay tight enough to appear as a coherent coma and anti-tail, rather than dissipating into a diffuse, undetectable cloud? These are fair questions, but they rest on assumptions about typical debris behaviour. What if 3I-ATLAS isn't typical? What if it came from an environment where debris fields can be more stable than we expect? What if its interstellar origin means it experienced conditions during formation that our solar system analogues never did? Or, and this is the part that makes everyone squirm, what if the swarm wasn't naturally formed at all? Loeb doesn't quite say it outright in most of his public statements, but the implication is there. If this is a swarm, if the fragments are inert and trailing, if the nucleus is experiencing clean acceleration, you have to ask, what sequence of natural events produces that configuration? Collisional breakup, tidal disruption, outgassing-induced fragmentation? All possible, but all requiring very specific initial conditions. Or maybe, just maybe, 3I-ATLAS is a relic, a fragment of something larger, something that fragmented intentionally, or as part of a structure that's been slowly falling, apart over millions of years of interstellar travel. Maybe the swarm isn't debris from a natural breakup. Maybe it's the remains of something built, something designed, something that's been drifting through the galaxy long enough that we can't even guess at its origin. That's the quiet part Avi Loeb said out loud, and now we all have to deal with it. Part 4. The reflectivity paradox and the 99% problem. Here's something that doesn't add up. 3I-ATLAS is bright. Too bright, given what we think we know about its size. Observations from ground-based telescopes and space observatories show that most of the visible light coming from 3I-ATLAS isn't from a compact nucleus. It's from the coma, the diffuse halo surrounding it. And that creates a problem, because a coma shouldn't be that bright unless it's scattering an enormous amount of sunlight, which requires surface area, which requires either a huge amount of material or an extremely efficient scattering geometry. Let me break this down. A solid nucleus, let's say a few kilometers across, has a limited surface area. That surface reflects sunlight based on its albedo, its reflectivity. Even if it's fairly reflective, the total amount of light it can bounce back is constrained by its size. You can't reflect more sunlight than hits your surface. That's basic physics. But 3I-ATLAS's coma, the cloud around the nucleus, is contributing the majority of the observed brightness. For that to happen, you need much more surface area than a single solid body provides. You need particles, lots of them, tiny grains, each one reflecting a bit of sunlight, collectively creating a bright halo that dominates the photometry. Here's an analogy. Imagine shining a flashlight on a single rock. It reflects some light back at you. Now imagine shining that same flashlight on a cloud of tiny mirror fragments, billions of them, spread out over a large volume. Collectively, those fragments reflect far more light than the single rock, even if their total mass is much less. The key is surface area to mass ratio. Smaller fragments have more surface per unit mass, making them phenomenally efficient at scattering light. So if 3I-ATLAS has a bright coma, it needs a lot of small particles. But here's the problem. Those particles should be leaving. Radiation pressure should be pushing them away, forming a tail, dissipating them into space. Yet the coma remains relatively compact. The antitail is stable. The brightness persists. How? The swarm hypothesis offers an answer. If the coma isn't made of freely escaping dust grains but rather a gravitationally or dynamically bound cloud of fragments, they don't disperse as quickly. They stay near the nucleus or trail behind it in a coherent structure, continuously scattering sunlight without dissipating into a long tail. You get persistent brightness without requiring constant mass loss. Let's run a thought. Experiment. Suppose 3I-ATLAS consists of 1 trillion fragments. That's 10 to the 12th individual pieces. If each fragment is small, maybe sub-meter or even smaller, their combined surface area could easily exceed that of a single nucleus by orders of magnitude. If these fragments have even moderately high reflectivity, they could collectively produce 90 to 99% of the total observed light, with the nucleus itself contributing almost nothing to the brightness. This would explain the reflectivity paradox. You're not looking at a big icy comet with a massive coma of sublimating material. You're looking at a swarm of inert fragments, each one a tiny mirror, collectively creating an optical effect that mimics but isn't actually a traditional cometary coma. But here's where this gets tricky. For a swarm to remain coherent, to not immediately disperse under solar wind and radiation pressure, the fragments need to be either large enough that radiation forces are weak compared to their inertia, or moving slowly enough relative to each other that they stay gravitationally or kinematically bound. And that's hard to achieve naturally. Typical cometary dust grains are small, micron-sized. They get blown away almost instantly. For a swarm to persist, you'd need fragments that are larger, maybe centimetre scale or bigger, heavy enough that radiation pressure doesn't immediately scatter them. But then you run into another problem. How do you produce millions or billions of such fragments without a catastrophic breakup event? And if there was such an event, why are the fragments still relatively close together? These are questions without easy answers, but they point to something strange about 3I-ATLAS's structure. It's not behaving like a normal comet, where dust is continuously produced by sublimation and immediately blown away. It's behaving like something with a more stable architecture, something where the reflective material isn't transient but structural. And that raises uncomfortable possibilities. If the reflective material is structural, if the fragments aren't temporary dust but long-lived debris, then you're not looking at an active comet in the traditional sense. You're looking at something more like a rubble cloud. Or, if you're willing to follow the logic all the way to its unsettling conclusion, something more like a distributed system. There's another wrinkle. If these fragments exist, why don't we see them directly? Why haven't high-resolution images resolved discrete clumps or individual pieces? The answer might be resolution limits. Even our best telescopes struggle to resolve features at the distance of 3I-ATLAS. If the fragments are small, sub-meter or meter scale, they'd be far below our detection threshold. What we see as a smooth, diffuse coma could actually be countless unresolved fragments, their light blending together into an apparently continuous glow. Or maybe the fragments are there, but Their motion is so tightly correlated with the nucleus that they don't create obvious structure. If they're all moving on nearly identical orbits, sharing almost the same velocity, they'd appear from Earth as a single diffuse cloud, rather than a collection of discrete objects. The swarm would be invisible as a swarm, detectable only through its collective optical signature. This is the 99% problem. If most of what you're seeing isn't the nucleus but the swarm, then everything you thought you knew about the object's size, mass and composition is wrong. You're not observing a comet, you're observing a cloud pretending to be a comet. And that changes everything. Part 5. Competing Scientific Factions. The Plume. Camp versus the propulsion camp. Science doesn't happen in a vacuum. It happens through arguments, debates, competing models, and sometimes very polite but very pointed disagreements between researchers who are absolutely convinced the other side is wrong. 3I-ATLAS has sparked exactly that kind of split. On one side, you have what we'll call the plume camp. These are mainstream cometary scientists, people who have spent careers studying volatiles, sublimation physics, and outgassing dynamics. They look at 3I-ATLAS and see a weird comet, sure, but still fundamentally a comet. Something that can be explained within the existing framework of planetary science without invoking exotic mechanisms. The plume camp points to a recent peer-reviewed preprint that models 3I-ATLAS's non-gravitational acceleration using thermophysical outgassing. The authors simulate a nucleus with a mixture of carbon monoxide and carbon dioxide ices, realistic surface thermal properties, and rotation. They show that under certain conditions, this kind of composition can produce an outgassing pattern that generates a radial acceleration scaling roughly as 1 over r squared, matching observations. Crucially, they don't need a swarm to explain the acceleration. They don't need exotic physics. They need a nucleus between 0.5 kilometre and 3 kilometres in radius, a plausible volatile mix, and the patience to run detailed thermal models that account for sublimation rates at different temperatures and illumination angles. The math works. The model reproduces the data, and then there's the anti-tail. Another recent paper tackles that directly. The authors propose that the sunward extension isn't a debris trail, but a natural consequence of anisotropic ice grain sublimation. Here's the idea. As 3I-ATLAS warms, it produces ice grains, tiny particles of water ice, that sublimate slowly depending on temperature and sunlight exposure. If the geometry of the nucleus and its illumination create conditions where ice grains survive longer when they're on the sunward side, those grains accumulate preferentially in that direction, scattering sunlight and creating an apparent anti-tail. The model is clever. It explains the sunward glow without requiring a swarm, without requiring any unusual structure. It's just ice grains, standard cometary material, behaving in a slightly unusual but physically plausible way due to the specific geometry and thermal environment of this particular object. The plume camp sees these models as vindication. 3I-ATLAS might be strange, but it's not so strange that we need to abandon comet physics. It's just pushing the boundaries of what we thought comets could do, revealing that the parameter space is wider, the behaviour more varied than we'd previously appreciated. But here's where the other camp, the propulsion or swarm camp, pushes back. They don't dispute that the models work mathematically. They dispute whether those models are plausible. Because to fit the observations, you need a very specific set of conditions. You need just the right volatile composition, just the right nucleus size, just the right thermal properties and rotation state, just the right grain size distribution and sublimation asymmetry. Any one of these assumptions is reasonable, but all of them together? That starts to feel like fine-tuning. The swarm camp argues that when you have multiple anomalies, a stable anti-tail, a clean inverse square law acceleration, and a reflectivity paradox, trying to explain each one individually with increasingly specific assumptions might be missing the point. Maybe the object is fundamentally different. Maybe it's not a single solid body, but a system. Maybe the reason we can't fit it neatly into our comet models is because it doesn't belong in that category. They point out that no known comet has shown this exact combination of features. Plenty of comets have shown non-gravitational acceleration, but it's messy, variable, and clearly linked to jetting activity. Some comets have shown unusual tail geometries, but those are typically short-lived phenomena tied to specific viewing angles or transient dust release events. 3I-ATLAS displays persistent, stable, geometrically precise anomalies that challenge multiple aspects of comet theory simultaneously. And that's what makes this split so interesting. The Plume camp is defending the conservative position, the one that requires the fewest new assumptions. Extraordinary claims require extraordinary evidence, and they're saying the evidence isn't extraordinary enough to overturn decades of cometary science. The models work. Use them. The Swarm camp, meanwhile, is arguing that sometimes the simplest explanation isn't the most conservative one. If forcing the data into existing models requires stacking assumption upon assumption, maybe the simpler explanation is that the object is just different. Maybe it's a swarm, maybe it's a rubble cloud, maybe it's something else entirely. Some in the Swarm camp go further. They suggest the inert debris trailing 3I-ATLAS could be rocky, metallic, remnants of a larger structure that fragmented long ago. They speculate about interstellar origins, about objects that might have experienced collisional histories or formation environments radically different from anything in our solar system. A few, like Loeb, even hint at the possibility of artificial origin, though usually hedged with caveats about how speculative that is. Here's the stakes. If the Plume camp is right, 3I-ATLAS is an outlier, but not a paradigm breaker. It's a comet at the edge of known behaviour, interesting, but ultimately explicable. If the Swarm camp is right, 3I-ATLAS might be the first confirmed member of a new class of interstellar objects, things that don't fit our taxonomy, that challenge our definitions, that force us to expand our understanding of what's possible. You, watching this, get to be the judge. Does the conservative model strain credibility too far? Does it feel like we're forcing a square peg into a round hole? Or is the exotic interpretation jumping to conclusions, seizing on mystery where there might just be complex but natural physics? Either way, 3I-ATLAS is doing something no other observed comet has done, and that alone makes it worth paying attention to. Because whether it's a weird comet or something more, it's already rewriting the rules about what interstellar visitors can look like. Part 6. Forgotten Interstellar Outliers, the cases that never fit the models. Let's talk about the visitors we've seen before, because 3I-ATLAS isn't the first interstellar object to make astronomers uncomfortable. It's just the latest. First came 1I/Oumuamua in 2017, tumbling through the inner solar system at enormous speed, moving on a clearly hyperbolic orbit that proved it came from interstellar space. It was unlike anything we'd seen, elongated, no visible coma, no tail, and yet somehow experiencing a small but measurable non-gravitational acceleration as it receded from the sun. Outgassing was the obvious explanation, except there was no visible outgassing. No dust tail, no gas emission lines, nothing. Just a mysterious push that made its trajectory deviate slightly from pure gravity. Scientists scrambled to explain it. Some proposed exotic compositions, hydrogen icebergs, nitrogen snow. Others suggested it was tumbling in just the right way to hide its activity from our telescopes. And a few, notably Loeb, suggested it might not be natural at all. That hypothesis got him mocked in some circles, praised in others, but mostly it made everyone deeply uncomfortable because it violated an unspoken rule. We don't talk about artificial origin unless absolutely forced to. Then came 2I/Borisov in 2019. This one looked more like a proper comet. Fuzzy coma, clear outgassing, a composition that seemed familiar, mostly water ice and carbon-bearing molecules. Scientists breathed a sigh of relief. See? Interstellar comets are just comets. Nothing weird here. Borisov behaved itself, followed the rules, and everyone felt reassured that the universe made sense again. Except Borisov had oddities too. Its carbon monoxide to water ratio was unusual, higher than typical solar system comets. Its coma showed structure that didn't quite match standard models, and its nucleus remained frustratingly unresolved, leaving questions about size and density unanswered. But compared to Oumuamua's strangeness, Borisov seemed normal enough that most researchers filed it under interesting but explicable. And now we have 3I-ATLAS, a sunward anti-tail, clean inverse square law acceleration, reflectivity that doesn't match expectations, an object that seems to combine features of both previous visitors, comet-like in some ways, anomalous in others, refusing to fit neatly into either category. 3 confirmed interstellar objects, 3 completely different behaviours. That should tell us something. It tells us our models might be too narrow. We've been assuming that interstellar visitors should behave like solar system small bodies, just with different orbits. But what if that assumption is wrong? What if objects that survive ejection from their home systems, that endure millions of years in the interstellar medium, that withstand cosmic ray bombardment and extreme temperature swings, are fundamentally different from the comets and asteroids we're used to? Think about selection bias. We can only detect interstellar objects that are big enough, bright enough, or pass close enough to Earth that our surveys pick them up. That means we're seeing a very specific subset: the survivors. The ones with enough mass or structural integrity to remain intact over interstellar distances. The ones that happen to be reflective enough to catch sunlight when they pass through. The ones whose trajectories bring them near enough for detection. How many interstellar objects pass through the solar system undetected? How many are too small, too dark, or on trajectories that keep them far from the Sun and Earth? We have no idea. Our sample size is 3. Making sweeping generalizations from 3 examples is absurd, but it's all we have. And yet, even with just 3 objects, we see enormous diversity. That suggests the true population is far more varied than our theoretical models predicted. Maybe interstellar space is full of rubble clouds, fragment swarms, exotic compositions, unusual structures. Maybe the reason Oumuamua, Borisov, and 3I-ATLAS all seem weird in different ways is because they are weird. Maybe weird is the norm for interstellar visitors, and our expectations are what's wrong. Consider the statistical improbability of what we're seeing. Based on estimates of planetary system formation and ejection rates, objects the size of 3I-ATLAS should be rare. Really rare. The fact that we've detected one at all suggests either we're incredibly lucky, or our models of how many interstellar objects exist are dramatically wrong. If the galaxy is full of large interstellar wanderers, that changes our understanding of planetary system dynamics, ejection mechanisms, and the overall architecture of star formation regions. There's another angle here. Until Oumuamua, we had no confirmed interstellar objects. 0. Our theories about what they should look like were pure speculation, based on models of planetary system formation and ejection processes that we'd never actually tested. We assumed interstellar objects would be similar to Oort cloud comets, because they'd form in the outer regions of exoplanetary systems before being ejected. We assumed they'd be icy, primitive, largely unchanged since formation. But reality, as usual, is more complicated. Oumuamua wasn't obviously icy. Borisov was icy but chemically unusual. 3I-ATLAS might be a swarm of fragments. None of them match the simple picture we had in our heads. And that's a lesson. Nature doesn't care about our simplifying assumptions. The universe is under no obligation to be easy to understand. So maybe it's time to adjust our framework. Maybe interstellar objects shouldn't be treated as a homogeneous class. Maybe they represent diverse histories, collisional fragments, ejected planetesimals, disrupted binary systems, even artificial constructs if we're willing to consider that possibility. Trying to force them all into a single category labelled interstellar comet might be as misguided as trying to describe all flying things as birds. 3I-ATLAS might be signalling that we need a new taxonomy, not just comet versus asteroid, but categories we haven't named yet. Swarm objects, rubble clouds, distributed systems, things that don't behave like single solid bodies because they aren't single solid bodies. And if that's true, if the interstellar population is genuinely diverse and strange, then we've been looking at the universe through a very narrow lens. 3I-ATLAS isn't an error, it's a clue, a signal that reality is richer than our textbooks suggest. Part 7. Hidden physics candidates, radiation pressure devices, hollow objects, and sail-like bodies. Let's get speculative, but responsibly speculative, grounded in physics speculative. What if 3I-ATLAS isn't a solid chunk of ice and rock? What if it has a structure we don't typically consider when thinking about comets? What if its shape, density, or architecture makes it respond to solar radiation in ways that mimic but aren't actually comet outgassing? Consider a hollow object, or an extremely low-density aggregate, or a porous structure so full of voids that its effective density is a tiny fraction of solid rock or ice. Such an object would have a very high surface area to mass ratio, and that matters because radiation pressure, the force exerted by sunlight hitting a surface, depends on area. Gravity depends on mass. If you maximize area while minimizing mass, radiation pressure becomes a significant force potentially strong enough to produce measurable acceleration. This isn't fantasy. Solar sails, proposed for interstellar probes, work on exactly this principle. A large, thin, reflective surface catches sunlight and gets pushed, generating thrust without propellant. The acceleration is small but continuous, and it scales inversely with distance squared from the Sun, exactly like gravity. Ring a bell? Now, I'm not saying 3I-ATLAS is a solar sail, but consider the possibility that it could have sail-like properties without being an engineered device. What if it's a natural structure, maybe a fragment of a larger object that happens to have a large, thin, reflective surface? What if it's a sheet of material, kilometers across but only meters thick, created by some exotic formation process we don't understand? Or consider fractal dust clouds, aggregates where tiny grains cluster together in a loose, fluffy structure with enormous internal voids. These exist in our solar system, in protoplanetary disks and comet tails. If 3I-ATLAS was such an aggregate, it could be physically large but incredibly low mass, with most of its volume being empty space. Sunlight pressure on all those tiny grain surfaces would add up, producing a net force that could look like propulsion. The physics here isn't controversial. Low-density, high-area structures do experience significant radiation pressure. The controversial part is suggesting that an interstellar object might have such a structure. Because how would it form? How would it survive? How would it stay intact over millions of years of interstellar travel, through cosmic ray impacts, through the tidal stresses of passing near stars or planets? These are good questions, and they don't have easy answers, but absence of an explanation isn't the same as impossibility. Maybe formation mechanisms exist that we haven't thought of. Maybe certain configurations are more stable than we assume. Maybe 3I-ATLAS survived precisely because it has an unusual structure that we can't easily account for. Let's talk about observational constraints. Why haven't we ruled out these exotic shapes? Because our observations are limited. We can't resolve the nucleus of 3I-ATLAS. We can't directly image its shape. What we see is its brightness, its colour, its coma, its trajectory. From that we infer size and structure, but those inferences depend on assumptions. If the assumptions are wrong, if it's not a solid ellipsoid but something more complex, our size estimates could be wildly off. Polarimetry could help. Light reflected from a solid surface shows different polarization than light scattered by a diffuse cloud or reflected from a thin sail. If 3I-ATLAS were a sail or sheet structure, we'd expect unusual polarization signatures. Similarly, detailed light curves, brightness variations as the object rotates, could reveal non-spherical shapes or surface features. So far, we don't have enough data to say definitively. Here's a thought experiment. Suppose 3I-ATLAS is a disk or sheet, oriented nearly face onto Earth. Sunlight hits it, reflects, produces brightness. But because it's face on, we don't see it edge on, so we can't tell it's thin. As it moves closer to perihelion, solar heating would increase. If it's truly a thin structure, that heating might cause warping, buckling, or even partial fragmentation. We'd expect to see changes in brightness, colour shifts as thermal emission becomes significant, maybe even structural breakdown. Did we see any of that? We have limited photometric coverage around perihelion, but nothing obviously catastrophic was reported. That could mean it's not a thin structure, or it could mean it's made of something surprisingly heat-resistant, or it could mean we weren't looking closely enough at the right times. The sail hypothesis has another implication: directionality. A sail's thrust depends on orientation. If 3I-ATLAS were a sail tumbling randomly, its acceleration would vary as different parts of the surface face the Sun. But if it's somehow oriented, maintaining a relatively stable attitude, the thrust would be more consistent. That sounds implausibly like control, which is why this hypothesis makes people so uncomfortable. But consider this. What if it's not active control but passive stability? Some spacecraft designs use spin stabilization, or natural orientation effects to maintain attitude. A thin object with asymmetric mass distribution might naturally orient itself relative to the Sun due to radiation torques or tidal effects. It's not beyond physics, it's just unusual. And that brings us to the elephant in the room. If 3I-ATLAS has sail-like properties, if its structure produces clean acceleration under sunlight, we have to at least consider the possibility that it's artificial, a relic, a fragment of something built, something launched, something that's been drifting for so long that its origin is lost to time. I want to be clear, there's no direct evidence for this, no signals, no markings, no behaviour that screams technology. But the combination of unusual acceleration, stable geometry, and reflectivity that doesn't fit natural models creates a set of characteristics that, if found in a human-made object, would be instantly recognizable. We're not saying it is artificial. We're saying the hypothesis is physically plausible enough that dismissing it without investigation would be intellectually irresponsible. What would we need to confirm or rule out these exotic hypotheses? Better imaging, radar observations if possible, detailed spectroscopy to look for unusual materials or surface compositions, long-term monitoring to see if the acceleration changes or remains perfectly consistent, polarimetry to test for sail-like reflection. All of this is technically possible. The question is whether we'll do it, or whether 3I-ATLAS will fade from view, leaving us forever uncertain. Part 8. The swarm as an orbital architecture, natural rubble cloud or engineered fragmentation layer. Let's assume, just for argument, that the swarm hypothesis is correct. 3I-ATLAS is a nucleus plus a cloud of trailing fragments. What does that actually mean? What are the dynamics? Can such a system stay coherent, or would it disperse immediately? To answer that, we need to think about how swarms behave in space. Start with the basics. Gravitational binding. A swarm of fragments will stay together if their mutual gravitational attraction is strong enough to overcome dispersive forces. But here's the problem. If the fragments are small and spread over thousands of kilometers, their self-gravity is negligible. They're not holding themselves together by gravity. So what is? One possibility. They're not held together at all. They're simply comoving. All the fragments were ejected from a parent body with similar velocities, so they're all on nearly identical orbits. From far away they look like a coherent cloud, but in reality they're just a bunch of independent objects that happen to be travelling together. Think of them as a flock of birds, but without any coordination or communication, just coincidental parallel paths. If that's the case, the swarm will slowly disperse over time. Small differences in velocity, minor perturbations from solar radiation pressure, interactions with solar wind, all of these will cause the fragments to drift apart. Eventually, the cloud spreads out so much that it's no longer detectable as a distinct structure. It becomes part of the background noise of interplanetary debris. But here's the catch. We're seeing 3I-ATLAS months after perihelion, and the anti-tail is still there. If the swarm were dispersing rapidly, we'd expect the structure to be changing, fading, becoming less distinct. But the observations suggest stability. That implies either the dispersion timescale is longer than we'd naively expect, or something is holding the swarm together more effectively than random initial velocities would allow. Maybe the fragments are larger than we're assuming. If they're meter scale or bigger, radiation pressure is weak compared to their inertia. They drift apart slowly, taking years or even decades to fully disperse. During that time, they'd remain visible as a coherent cloud, especially if they're reflective. Or maybe the fragments aren't purely passive. Maybe there's residual outgassing, not from the fragments themselves, but from the nucleus. And that outgassing creates a tenuous gas envelope that applies drag to the fragments, keeping them closer together than they'd otherwise be. It's a weak effect, but over months it might be enough to delay dispersion. There's another scenario, more speculative but worth considering. What if the swarm isn't the result of a random breakup but a structured release? Imagine a parent body that, deliberately, or through some natural process, ejected fragments at specific velocities and angles, creating a cloud with correlated orbital parameters. Such a configuration could remain coherent for longer, because the fragments weren't just randomly scattered, but placed into a stable dynamical arrangement. That sounds artificial, I know, but certain natural processes could mimic it. Rotational breakup, where a rapidly spinning object sheds material from its equator, might produce a disk or cloud of fragments with similar orbits. Tidal disruption, if 3I-ATLAS passed near a massive body before entering our solar system, could stretch and fragment it, leaving a stream of debris along its orbit. Now let's talk about composition. For the swarm hypothesis to work, the fragments need to be non-volatile. If they were ice, they'd sublime, produce outgassing, and experience forces that would push them around, breaking up the coherence, so they're probably rocky, maybe carbonaceous, possibly metallic. That raises a question. What natural process produces a comet nucleus surrounded by inert, non-volatile debris? One answer, collisional fragmentation. 3I-ATLAS could be the remnant of a larger body that collided with something in interstellar space, shattering into pieces. The largest piece became the nucleus, while smaller fragments trail behind, held in a loose orbital configuration by their shared history. Over time, volatile ices on the fragments sublimed away, leaving only the rocky cores, which don't outgas and therefore remain passive. Another answer: thermal processing. If 3I-ATLAS spent time near a star before being ejected, intense heating could have driven off volatiles from surface layers, leaving a refractory crust. If that crust then fragmented due to thermal stress or impacts, you'd get rocky, non-volatile debris without requiring a catastrophic collision. Or, if we're willing to go further, consider an artificial origin. Maybe 3I-ATLAS is the remnant of a large structure, a spacecraft or space station, that fragmented over time due to impacts, radiation damage, or structural failure. The fragments would be metallic or composite materials, non-volatile by design, and might remain loosely associated due to initial orbital parameters. This is speculative, yes, but physically consistent with what we observe. What observational test could confirm or falsify the swarm hypothesis? First, high-resolution imaging over time. If the antitail's shape changes, if it disperses or shows clumping, that tells us about the dynamics of the fragments. Second, photometric variations. If fragments occasionally occult the nucleus or each other, we'd see brief dips in brightness, flicker events that would be a strong signature of discrete objects. Third, polarimetry and spectroscopy. Different materials polarize and reflect light differently. If the coma and antitail have different spectral or polarization properties than you'd expect, from ice grains that's evidence for something unusual. Fourth, radar. If any of the fragments are large enough and 3I-ATLAS ever passes close enough to Earth, radar could resolve them directly, measuring their size, shape and velocity. That would be definitive. The problem is we're running out of time. 3I-ATLAS is moving away, getting dimmer, harder to observe. If we don't gather this data soon, the chance will be lost, and we'll be left with tantalizing hints but no proof. Here's the philosophical implication. If swarms like this exist, if interstellar space contains not just single objects but distributed systems, our entire approach to detecting and characterizing small bodies needs to change. We can't just look for compact point-like objects. We need to search for diffuse structures, extended halos, dynamical signatures of multiple components moving together. We might have been missing entire classes of interstellar visitors simply because we weren't looking for the right thing. Part 9. The shadow data. What observations haven't been released yet? There's something we need to talk about. The data we have on 3I-ATLAS is good, but it's incomplete. There are gaps, observations that were made but not publicly released, measurements that didn't make it into papers or press releases, and in those gaps might lie the answers to the questions we're asking. So let's talk about what we know we have. Astrometric observations, positions measured over time, used to compute the orbit and detect non-gravitational acceleration. We have those, or at least the aggregated results from fitting models to them. We have imaging from ground-based telescopes showing the coma and the antitail. We have some photometry, brightness measurements over time, though not as complete as we'd like. We have spectroscopy showing gas emission lines, detections of carbon monoxide, cyanide, traces of other volatiles. We have polarimetric data from some observatories, though again, limited. Now let's talk about what we don't have. High-resolution time series imaging. The kind that would let us watch the coma's structure change over hours or days, revealing whether there are discrete clumps, whether fragments are moving independently, whether the antitail's geometry is stable or evolving. That data exists. Telescopes took those images, but they're not in the public domain, not analysed in published papers, not accessible to independent researchers who might have different interpretations. We also don't have detailed residuals from the orbital fits. When you model an orbit, you're left with residuals, the differences between predicted and observed positions. If those residuals are large or show structure, it might indicate the object isn't a single point mass but something more complex. Multiple components would produce systematic offsets or scatter that wouldn't fit a simple comet outgassing model. But those residuals aren't published. We get the fit parameters, but not the raw data showing how good or bad the fit actually is. Multi-wavelength observations are patchy. We have visible light imaging, some infrared, but not comprehensive coverage across the spectrum. Infrared is crucial because it probes thermal emission, which could tell us about composition, surface temperature, particle sizes in the coma. Radio observations could detect larger dust particles, or even measure radar reflections if the object ever came close enough. But this data either doesn't exist or hasn't been shared. Long-term monitoring is also lacking. After perihelion, observations became less frequent. 3I-ATLAS is dimmer now, harder to observe, and telescope time is expensive. But watching how the anti-tail evolves, whether it fades, whether fragments disperse, whether the brightness drops faster or slower than predicted, all of that would constrain models. Without it, we're guessing. Why does this matter? Because science depends on transparency. When observations are locked away, when only certain researchers have access, when data is selectively released to support a particular narrative, we lose the ability to independently verify claims. And worse, we might miss anomalies that don't fit the preferred interpretation. There's a historical precedent for this. Comets have a long history of anomalous observations that were quietly downplayed or explained away. Brightness outbursts attributed to measurement error. Orbital residuals dismissed as noise. Unusual spectral features ignored because they didn't fit models, not through malice, but through a very human tendency toward model sanitation. When data doesn't fit, it's tempting to tweak the calibration, adjust the error bars, or simply not publish it. I'm not accusing anyone of misconduct. But I am suggesting that 3I-ATLAS might be undergoing a real-time version of this process. As more data comes in, as models are refined, as non-gravitational parameters are adjusted, there's pressure to make the object fit existing categories, to smooth out the anomalies, to present a coherent picture that doesn't challenge too many assumptions. The problem is, 3I-ATLAS might be telling us something important precisely through its anomalies. If we sanitize the data, if we force it into models that don't quite fit, we might miss the message. So what data do we need? Everything. Raw astrometry with full error estimates. All imaging, not just the pretty pictures, but the full-time series showing every observation. Spectroscopic data across as many epochs and wavelengths as possible. Polarimetry, thermal infrared, radar if feasible. And most importantly, open access to all of it, so researchers outside the core observing teams can analyze it independently. This isn't just about 3I-ATLAS, it's about how we do science. In an era where every telescope generates terabytes of data, selective publication is easy, but it's also dangerous. It creates information asymmetries where only certain people can see the full picture, and everyone else has to trust their interpretation. If 3I-ATLAS is a swarm, if it's something exotic, if it's anything other than a standard comet, the evidence is in that shadow data. The observations that haven't been released, the measurements that didn't fit, the residuals that were too large, the images that showed structure nobody wanted to explain. We might never get that data. 3I-ATLAS is fading, observations are ending, and whatever wasn't captured is lost. But the lesson remains. Extraordinary objects require extraordinary transparency. If we're serious about understanding interstellar visitors, we can't cherry-pick the data that confirms our expectations. We need all of it. Part 10. The broader cosmic pattern. Visitors that don't behave randomly. Here's a question that should keep you up at night. What if 3I-ATLAS isn't unique? What if it's part of a pattern we're only just starting to see? Think about our detection rate. 3 confirmed interstellar objects in less than a decade. That's not a lot, but it's also not zero. And given how limited our surveys are, how much of the sky we're not watching, how faint these objects are, 3 detections might represent a much larger population passing through unnoticed. Some estimates suggest dozens or even hundreds of interstellar objects traverse the inner solar system every year. Most are too small, too dark, or on trajectories we don't happen to observe. We're sampling a tiny fraction of what's actually out there, and from that tiny sample, we found 3 very different objects. Oumuamua's mysterious acceleration, Bozhiov's weird chemistry, 3I-ATLAS's anti-tail and swarm hypothesis. 3 objects, 3 anomalies. That's not a coincidence, that's a pattern. Maybe the interstellar population is genuinely diverse. Maybe ejection from exoplanetary systems produces a wide variety of structures, solid bodies, rubble piles, fragment clouds, even things we don't have names for. Maybe the idea that interstellar objects should be uniform, should all behave like our solar system's comets, is the mistake. Consider where these objects come from. Exoplanetary systems, star-forming regions, maybe even stellar collisions or supernovae ejecta. The formation environments are wildly different from the quiet, stable conditions of our solar system's outer regions. Maybe that produces fundamentally different types of objects. There's another angle here: orbital alignment. 3I-ATLAS's trajectory is reportedly aligned within about 5 degrees of the ecliptic plane. That's unusual. Interstellar objects coming from random directions in the galaxy should have random orbital inclinations. They shouldn't preferentially lie near the ecliptic unless there's a reason. Maybe it's selection bias. Objects near the ecliptic are more likely to be detected because that's where most telescopes focus, where the planets are, where surveys concentrate. But that doesn't fully explain it. There's also the possibility of a source region. If many interstellar objects come from exoplanetary debris disks, which tend to be planar structures aligned with their host star's equator, then maybe ejected fragments preferentially arrive from certain directions, certain galactic orientations. Or maybe, and this is pure speculation, the alignment isn't random. Maybe 3I-ATLAS was placed, aimed, sent on a trajectory calculated to pass through systems with habitable zones. That sounds absurd, I know. But if we're entertaining the possibility of artificial origin, we can't ignore the possibility of intentional targeting. Let's step back. What does this all mean? If interstellar visitors are diverse, if many of them don't behave like standard comets or asteroids, our entire framework for understanding them needs revision. We can't just apply solar system small body physics and expect it to work. We need new categories, new models, new expectations, and that has implications beyond just catalogue entries. If the galaxy is full of strange objects, rubble clouds, swarms, maybe even relics of dead civilizations, then the cosmic environment is richer and more complex than we've imagined. The space between stars isn't empty, it's populated, and some of that population might be very old, very strange, and very different from anything we've encountered. 3I-ATLAS might be the wake-up call, the object that forces us to admit our models are too narrow, our assumptions too Earth-centric, our imagination too limited. It's not just a weird comet, it's a signal, a message from the universe saying, you don't know what's out there, start paying attention. Part 11. December 2025. New JWST and telescope findings. Small bodies, big surprises. Let's zoom out from 3I-ATLAS for a moment and look at what else is happening in small body science, because 2025 is turning into a year of surprises. The James Webb Space Telescope is revealing things about asteroids, comets, and trans-Neptunian objects that challenge our assumptions about surface chemistry, composition, and reflectivity. Sometimes the most important discoveries aren't the dramatic ones that make headlines, but the quiet accumulation of anomalies that forces an entire field to rethink its foundations. Recent JWST observations of several trans-Neptunian objects, those distant icy bodies beyond Neptune's orbit, show infrared spectra that don't match predictions. We expected water ice, maybe some methane or ammonia frost, signatures consistent with cold, primitive bodies that haven't changed much since the solar system formed. These objects orbit in the deep freeze, billions of kilometers from the sun, where temperatures hover just above absolute zero. They should be pristine, time capsules, frozen since the early days of the solar system, their surfaces barely modified by the weak sunlight that reaches them. Instead, we're seeing unusual absorption features, hints of complex organic molecules, maybe even surface processing that shouldn't happen at those temperatures, spectral lines that don't correspond to simple ices, chemical signatures that suggest active chemistry, reactions that require energy, transformations that shouldn't occur in the frozen outer reaches of the solar system. It's as if these objects have been cooking, processed by forces we don't fully understand, altered in ways that our models of cold, inert bodies can't explain. The leading hypothesis invokes cosmic rays, high-energy particles from supernovae and other violent events that permeate interstellar space and bombard everything they encounter. Over millions of years, this radiation can break chemical bonds, create free radicals, drive reactions that wouldn't happen thermally. It's slow cooking, radiation chemistry happening on geological timescales, gradually transforming simple ices into complex organic compounds. But the details are murky. We don't know exactly what reactions occur, what products form, or how the surface properties change as a result. Other small bodies throughout the solar system are showing unexpectedly high albedo, unusually bright surfaces that reflect more sunlight than models predict. For dark, primitive asteroids or distant comets, this is strange. These objects are supposed to be covered in organic tars, carbonaceous material, dark dust that absorbs most of the light hitting it. That's what we see in meteorites. That's what spacecraft missions to asteroids have confirmed. Dark surfaces, low reflectivity, albedos of 5 to 10% or even lower. But some objects don't follow the script. They're brighter than they should be, reflecting 20 or 30 or even 50% of the light hitting them. That suggests surface properties we don't fully understand, maybe grain structures that scatter light more efficiently, maybe ice halos that form through sublimation and redeposition, maybe compositions that include highly reflective minerals, or unusual organic compounds that don't behave like the carbonaceous material we're familiar with. Sound familiar? It should. 3I-ATLAS's reflectivity paradox, the fact that its coma seems brighter than a small nucleus should allow, isn't unique. It's part of a broader pattern where small bodies surprise us with how much light they reflect. The swarm hypothesis offers one explanation for 3I-ATLAS specifically, but the broader phenomenon suggests something more fundamental. Maybe our understanding of small body surfaces, the way dust and ice and organic material behaves in space, is incomplete. This matters because our models of small body surfaces are based on limited samples. We've visited a handful of comets and asteroids with spacecraft. We've analysed meteorites that fell to Earth, rocks that survived atmospheric entry and landed intact enough to study. We've observed thousands of objects telescopically, measuring their brightness and colours and spectra from afar. But those samples might not be representative. The spacecraft missions target objects that are accessible, relatively nearby, on orbits that allow rendezvous. The meteorites that reach Earth are biased towards strong, coherent rocks that can survive the violence of entry. The telescopic observations favour bright objects we can detect easily. If interstellar objects, trans-Neptunian objects, and distant comets have different surface properties due to cosmic ray exposure, different formation environments, or long-term radiation processing, then our assumptions about brightness, composition, and structure could be systematically wrong. We might be extrapolating from a biased sample, building models that work for the objects we've studied closely but fail for the broader population we've only glimpsed from afar. Think about 3I-ATLAS in this context. Maybe its unusual reflectivity isn't because it's a swarm of fragments, or at least not entirely because of that. Maybe it's because interstellar surfaces, exposed to millions of years of cosmic rays and interstellar radiation far from any star, develop unusual scattering properties. Radiation processing could alter grain structures, create surface textures that enhance reflectivity, produce compounds that scatter light more efficiently than solar system materials. The grains in its coma might have been altered in ways we don't see in solar system comets, making them more efficient at reflecting sunlight per unit mass. Interstellar space is not empty. It's filled with low-density gas, dust, and radiation. An object drifting through it for millions of years would accumulate a surface layer of interstellar material, get bombarded by cosmic rays, undergo sputtering and chemical alteration. By the time it enters our solar system, its surface might be fundamentally different from objects that formed here and stayed here. Different chemistry, different structure, different optical properties. We have no direct samples of such surfaces. We've never visited an interstellar object up close. All our understanding comes from remote observations and theoretical models based on solar system analogues. Or maybe both explanations are partly true. Maybe it's a swarm, and the fragments have unusual surfaces. Maybe the swarm architecture provides the large collective surface area that explains the overall brightness, while the unusual surface properties of individual fragments explain why each piece reflects more light than expected. The two effects could multiply, creating an object that's far brighter than any single explanation would predict. The point is, we're discovering that small bodies are more diverse, more complex and less well understood than we thought. 3I-ATLAS isn't an isolated anomaly. It's one example in a growing list of objects that don't fit our models. The trans-Neptunian objects with weird spectra are another. The unexpectedly bright asteroids are another. Each one, individually, can be explained away with some combination of special pleading and fine-tuned parameters. But collectively, they suggest our frameworks are incomplete. JWST is going to find more. As it observes more small bodies, more distant objects, more faint targets that ground telescopes can't reach, we're going to see more surprises. more unusual spectra that don't match laboratory measurements of known compounds, more unexpected compositions that hint at chemistry we don't fully understand, more things that make us question whether our textbook understanding of these objects is accurate. The telescope is so sensitive, so powerful in the infrared, that it can detect features previous instruments missed. It's not just observing objects we already knew about, it's revealing details about those objects that force us to reconsider what we thought we knew. And that's exciting, because every time our models break, we learn something. Every anomaly is an opportunity to expand our understanding, to discover new physics or new chemistry or new geological processes, to recognize that the universe is more interesting than we gave it credit for. Science doesn't progress through confirmation of existing theories. It progresses through the uncomfortable process of confronting observations that don't fit and figuring out what needs to change. 3I-ATLAS might be the most famous example right now, the one that generates headlines and debates and wild speculation about swarms and artificial structures. But it's not alone. It's part of a wave of discoveries that are collectively telling us small body science is entering a new era, an era where the exceptions might be more important than the rules, an era where the weird objects, the ones that don't fit our categories, teach us more than the well-behaved ones that confirm what we already believe. Consider what this means for the broader search for interstellar objects. If surfaces can be altered by interstellar radiation in ways we don't fully understand, if reflectivity can vary dramatically based on processing history and composition, then our ability to identify and characterize interstellar visitors is compromised. We might be missing objects because they're too bright or too faint compared to our expectations. We might be misidentifying them as asteroids or comets based on properties that turn out to be misleading. The solution is more observations, more detailed spectroscopy, more missions to small bodies that can measure surface properties directly. We need to build a library of what's actually out there, not what we think should be out there. We need to observe objects at all distances, from near-Earth asteroids to trans-Neptunian objects to interstellar visitors, and catalogue their properties without forcing them into preconceived categories. JWST is one tool in that effort. Ground-based telescopes with adaptive optics are another. Future missions to comets and asteroids, including proposed missions to interstellar objects if we can catch one in time, would provide crucial ground truth. And perhaps most importantly, we need to remain intellectually humble, willing to admit when our models fail and eager to build better ones. 3I-ATLAS is a test case. It's weird enough to demand explanation, visible enough that we can't ignore it, and controversial enough that multiple competing theories are being actively debated. That's healthy. That's how science should work. And as we wrestle with what 3I-ATLAS means, as we try to reconcile its properties with our understanding of comets and interstellar objects, we're also being forced to confront the broader question of whether our understanding is adequate. The answer increasingly seems to be no. Our models work for the well-studied, well-behaved objects, but they struggle with the outliers, the anomalies, the weird cases that don't fit. And if JWST keeps finding more such cases, if the population of anomalous objects grows faster than our ability to explain them away, we'll eventually reach a tipping point where the models have to change. Maybe that tipping point is now. Maybe 2025 is the year we look back on as the moment when small body science broke its old frameworks and started building new ones. 3I-ATLAS is part of that story. But so are the trans-Neptunian objects with unexpected chemistry. So are the asteroids with surprising reflectivity. So are all the quiet, unglamorous observations that don't make headlines, but collectively paint a picture of a universe more complex than our textbooks suggest. An era where the exceptions might be more important than the rules, where the strange objects teach us more than the ordinary ones, where anomalies aren't problems to be solved but opportunities to be embraced. 3I-ATLAS might be leading that charge, but it's not marching alone. The whole field is moving slowly and reluctantly perhaps, but moving nonetheless toward a broader and stranger understanding of what's out there in the dark. Part 12. Breakthrough in solar sail and photonic film experiments. Tiny surfaces, big forces. While astronomers debate 3I-ATLAS, materials scientists and aerospace engineers have been making breakthroughs of their own. Developments in ultra-thin photonic films, metamaterials and solar sail technology that, oddly enough, might be relevant to understanding interstellar visitors. Sometimes the most important connections happen at the boundaries between disciplines, where nobody's really looking. Recent experiments with nanometer-scale reflective films have demonstrated something surprising. Under intense light flux, these materials can exhibit nonlinear photon pressure effects. The thrust-to-mass ratio, the acceleration per unit mass produced by light pressure, can be significantly higher than classical radiation pressure theory predicts. Not by a lot, we're not talking about magic or physics-breaking discoveries, but enough to matter. Enough that when you start scaling up from laboratory samples to kilometre-scale objects in space, the difference becomes noticeable. Part of this comes from metamaterial design, structures engineered at wavelengths comparable to visible light that can manipulate photons in unusual ways. Researchers have created films that don't just reflect light but redirect it, focusing momentum transfer in specific directions, effectively amplifying the thrust produced by a given amount of sunlight. It's not perpetual motion or free energy, it's just clever engineering. You're not getting more photons, you're just extracting more momentum from the ones you have by controlling exactly how they bounce off your surface. The physics is subtle but important. Classical radiation pressure assumes photons hit a surface and bounce off uniformly, transferring momentum according to simple conservation laws. But if you engineer the surface at the nanoscale, creating patterns and structures that interact with specific wavelengths, you can bias the reflection angle, concentrate the momentum transfer, and effectively get more push per photon. It's like the difference between a flat mirror and a parabolic reflector. Same light source, different geometry, different results. Why does this matter for 3I-ATLAS? Because it demonstrates that with the right structure, even without exotic physics, you can get more acceleration from sunlight than naive models would suggest. If 3I-ATLAS happened to have a surface or structure, natural or otherwise, that enhances photon momentum transfer, that could explain its clean, persistent acceleration without requiring massive outgassing. You wouldn't need jets of gas shooting in precisely the right direction. You'd just need a surface that interacts with sunlight in a particular way. This isn't saying 3I-ATLAS is a solar sail, let's be clear about that. But it's saying the physics of solar sails, the way thin structures with high area-to-mass ratios respond to light, might apply to natural objects too. If an interstellar body formed with a fractal, porous or sheet-like structure, if it went through some chaotic formation process that happened to produce sail-like geometry, it could accidentally have sail-like properties. Nature doesn't optimize for anything in particular, but it explores an enormous parameter space. Occasionally it stumbles onto configurations that look engineered even when they're not. Think about it. Solar sails are designed to maximize thrust per unit mass. They're thin, reflective, have enormous surface area relative to their weight. If nature, through some chaotic process, collisions, thermal processing, fragmentation events, whatever, produced a structure with similar properties, it would behave similarly. It would experience persistent acceleration scaling as 1 over r squared, exactly matching the inverse square law of solar intensity. It would be bright relative to its mass, reflecting a lot of sunlight for its weight. It would look, from our observations, a lot like 3I-ATLAS. The challenge is survival. This is where the hypothesis gets tested against reality. Spacecraft solar sails are engineered to withstand radiation, micrometeorite impacts, thermal stress. They're made from carefully selected materials tested in vacuum chambers, designed with redundancy and fault tolerance. A natural object with sail-like properties would be fragile. Could it survive interstellar travel? Could it endure the radiation environment between stars, the cosmic rays, the occasional dust grain impact at tens of kilometers per second? Could it survive near perihelion heating, temperatures that would vaporize ice and sublimate many compounds? These are open questions, and they cut both ways. On one hand, survival seems unlikely. Anything thin enough and light enough to have high thrust to mass would be vulnerable to destruction. But on the other hand, we're seeing 3I-ATLAS right now. It exists. It survived whatever journey brought it here. So either it's not as fragile as we think, or there are structures and materials we haven't fully considered. Recent simulations suggest that certain porous, fractal structures might be more robust than expected. The voids provide insulation, reducing thermal stress. Instead of heat conducting through solid material and causing catastrophic thermal gradients, it radiates away from surfaces, keeping temperatures more uniform. The distributed structure means local damage doesn't cause catastrophic failure. You can punch holes in a fractal aggregate and it keeps functioning, keeps holding together because no single component is critical. And if the material is refractory, high-temperature ceramics or carbon compounds, graphite-like structures or silicate minerals, it might survive conditions that would vaporize ordinary ice. We're used to thinking of comets as icy, volatile-rich objects. But what if some interstellar visitors are the opposite? What if they're refractory, composed of materials that can withstand high temperatures, materials that formed in violent environments or were processed by previous stellar encounters? There's another implication here, one that deserves more attention than it usually gets. If solar cell technology is advancing to the point where we can build ultralight, high-thrust structures that can cross interstellar distances given enough time, maybe other civilizations have done the same. Maybe thousands of them. Maybe millions. The galaxy is billions of years old. Stars have been forming and dying. Planets have been forming around those stars, and presumably some fraction of those planets develop civilizations. If even a tiny percentage of those civilizations develop spaceflight, if even a fraction of those launch interstellar probes, the cumulative effect over billions of years could be substantial. Maybe interstellar space is littered with old probes, derelict light sails, fragments of missions launched millions of years ago and long since forgotten by the civilizations that built them. Probes that have been drifting through the void, pushed by starlight, occasionally passing through stellar systems, occasionally catching the light of a new sun, and experiencing a brief moment of acceleration before drifting back into darkness. A defunct solar sail tumbling through space would look a lot like a comet. It would reflect sunlight, possibly brightly if its surface is still intact and retains its reflective properties. It would experience acceleration from radiation pressure, producing clean, persistent thrust that scales with solar intensity. It wouldn't outgas, wouldn't have a dust tail in the conventional sense, but it might have fragments trailing behind if parts of the structure broke off over time. It might have a swarm of debris, pieces that separated from the main body through collisions or structural failure or deliberate design. I'm not claiming 3I-ATLAS is an alien probe. Let me be absolutely clear about that. The evidence doesn't support that conclusion, and the natural explanations, while strained, are still plausible. But I am saying the hypothesis is physically consistent with what we observe. And if we're developing solar sail technology ourselves, if we're planning missions like Breakthrough Starshot that would send tiny light-propelled probes to nearby stars, it's not unreasonable to think others might have tried the same thing. The physics is universal. The engineering challenges are universal. If it's possible for us, it's possible for them. The philosophical angle here is sobering. If sunlight can push objects across interstellar distances, if all you need is a thin reflective surface and enough time, then the universe might contain countless such objects, drifting silently between stars, some natural, some artificial, most undetected because we're not looking for them. Our surveys are optimized for finding asteroids and comets that behave in predictable ways, objects that have high area-to-mass ratios, that accelerate in unusual patterns, that don't fit our taxonomies, get filtered out or ignored. But what if there are thousands of them? What if right now there are defunct light sails passing through the outer solar system, too faint to detect, too far away to characterize, drifting through on trajectories that will carry them past the sun and back into interstellar space? What if the galaxy is full of such objects, a vast fleet of forgotten machines and natural analogues, all responding to starlight, all drifting on currents we barely understand? 3I-ATLAS might be one such object, or it might just be the first natural example that makes us realize how easy it is to mistake one for the other. The boundary between natural and artificial becomes fuzzy when you're talking about structures optimized by physics rather than biology. A solar sail optimized for thrust looks a certain way because physics demands it. A natural structure that happens to have similar properties looks the same way for the same reason. Without detailed analysis, without getting close enough to examine surface features and material composition, telling them apart becomes very difficult. And maybe that's the real lesson here. Maybe 3I-ATLAS is teaching us that the universe doesn't care about our categories, our neat divisions between natural and artificial, between comet and probe, between object and system. Maybe it's showing us that reality exists on a spectrum, and we've been looking at only one narrow slice of it, because that's all our instruments and theories were designed to see. The solar sail experiments continue. Engineers are building bigger, lighter, more efficient designs. Materials scientists are developing new films, new coatings, new structures that squeeze every bit of momentum out of every photon. And while they work, 3I-ATLAS drifts outward, moving away from the sun, carrying its secrets with it. Maybe it's natural, maybe it's not. But either way, it's forcing us to think harder about what's possible, what's out there, and what we might be missing. Because if sunlight can move mountains given the right geometry, then the universe is full of mountains we haven't noticed yet, and some of them might be coming our way. Part 13. The AI-driven discovery, mining 30 years of comet data for hidden patterns. Here's something that should terrify and excite you in equal measure. We might have been missing anomalies for decades simply because we weren't looking for them properly. A research team recently applied machine learning algorithms to archival comet and asteroid astrometry, 30 years of orbital data from thousands of objects. The goal was simple: identify objects whose motion deviates from purely gravitational predictions in ways that existing models don't explain. Feed the algorithm decades of position measurements, orbital fits, and residuals. Let it search for patterns that human astronomers, working within the constraints of their theoretical frameworks, might have overlooked or dismissed. What they found was unsettling. A small but non-zero fraction of catalogued objects showed persistent orbital residuals, deviations that couldn't be fully explained by standard comet outgassing models. These weren't dramatic deviations, not the kind that jump out at you when you plot an orbit. These were subtle, consistent, statistically significant anomalies that appeared when you looked at the data with fresh eyes and no preconceptions. These objects didn't have visible comae or tails, so they'd been classified as asteroids. But their orbits were slightly wrong, consistently wrong, in ways that suggested non-gravitational forces acting on them over extended periods. Most of these anomalies were ignored, labelled as measurement noise, poor astrometry, or insufficient data. When your orbit-fitting software spits out residuals that don't quite match the model, you have options. You can flag it for follow-up observation, you can dig deeper into the dynamics, or you can assume your measurements were noisy, your telescope tracking was off, or the object just doesn't have enough data points for a clean fit. The third option is easiest. It's how science actually works in practice. When you're dealing with thousands of objects and limited resources, you prioritise the ones that matter, the ones that look interesting, and you let the marginal cases slide. But when the AI flagged them as statistically significant, when patterns emerged across multiple objects observed by different telescopes over different epochs, it became clear that something was being missed. The algorithm didn't care about theoretical expectations or resource constraints, it just looked at numbers, and the numbers said some of these objects were experiencing forces that shouldn't be there, according to the standard gravitational plus outgassing models we use for orbit determination. Maybe some of these are just bad data. That's always possible, always the conservative explanation. Astrometry is hard. Measuring the position of a faint object moving against background stars, correcting for atmospheric distortion and telescope tracking errors and catalogue uncertainties introduces noise. Stack up enough noisy measurements and you'll get residuals that look meaningful but aren't. Statistical flukes happen. The universe is under no obligation to make sense just because an algorithm flagged something. But maybe some are real. Maybe there's a hidden population of objects in our solar system and passing through it that experience subtle accelerations we don't account for. Objects without visible activity but with dynamics that hint at something we don't understand. Objects that don't fit our taxonomy because we built our taxonomy around the objects we could see clearly, the ones with obvious signatures, and ignored the ones that operated at the margins of our detection capabilities. Think about what this means for a moment. We've been surveying the solar system for over a century, cataloguing asteroids and comets with increasing precision. We have orbital data on hundreds of thousands of objects. We think we understand the population statistics, the size distributions, the dynamical families. But all of that understanding is built on objects that fit our models. If there's a population of objects that don't fit, that operate according to different rules, or have different compositions or experience forces we haven't properly characterized, we would have systematically excluded them from our analysis without even realizing it. 3I-ATLAS might be the first interstellar example of this class, but if the AI analysis is right, it's not alone. There might be dozens or hundreds of similar objects, quietly defying our models, going unnoticed because we focus on the ones that look active, that have comae and tails and fit our expectations. We search for what we know how to find. We classify what we know how to classify. Everything else gets filtered out, not through malice or incompetence, but through the simple fact that we can't investigate every marginal case, every weird residual, every object that doesn't quite fit. This has huge implications for how we search for interstellar visitors. Current surveys prioritize objects that look unusual, fast-moving, bright, with hyperbolic orbits that immediately scream, "Not from around here." We found one I-Oumuamua because it was moving fast on a clearly unbound trajectory. We found 2I Borisov because it had a coma and looked like a comet, but was on a hyperbolic orbit. We found 3I-ATLAS because it was bright enough and weird enough to warrant attention. But what if many interstellar objects don't look unusual? What if they masquerade as asteroids, dark and inactive, and only their dynamics give them away? An interstellar visitor moving slowly on a trajectory that's only slightly hyperbolic, without obvious outgassing or a bright coma, would be almost impossible to distinguish from a solar system asteroid using visual observations alone. You'd need to measure its orbit very carefully, accumulate enough data points to establish that it's not gravitationally bound to the Sun, and even then you might dismiss small deviations as measurement error. How many such objects have we already observed and misclassified? How many are in our catalogues right now, labelled as asteroids, their true nature hidden because nobody checked their dynamics carefully enough? The AI approach flips the script. Instead of looking for visual anomalies, look for dynamical anomalies. Scan orbital data for deviations, even subtle ones that don't fit. Flag objects that experience forces we can't explain. Follow up with spectroscopy, imaging, polarimetry to figure out what they are. It's a fundamentally different search strategy, one that doesn't rely on objects announcing themselves with obvious visual signatures. It's slower, more computational, requires more follow-up resources, but it might be the only way to find the objects that operate quietly, the ones that don't scream for attention but still tell us something important about the universe. If we did this systematically, if we applied these algorithms not just to archival data, but to ongoing surveys, we might discover that interstellar visitors are far more common than we thought. They're just hiding in plain sight, misclassified as ordinary asteroids because nobody bothered to check their orbits carefully enough. The Vera C. Rubin Observatory coming online soon will observe millions of objects. The Legacy Survey of Space and Time will generate petabytes of astrometric data. If we run AI anomaly detection on that data stream in real time, we could catch interstellar visitors while they're still in the inner solar system, still accessible for follow-up, still bright enough to characterize. And here's the unsettling part. If there's a hidden population of dynamically anomalous objects, what are they? Natural bodies with unusual outgassing that doesn't produce visible comae. Fragments with exotic compositions, maybe metallic or carbonaceous, that experience radiation pressure differently than rocky asteroids. Loosely bound rubble piles whose internal structure affects their dynamics in subtle ways, or in rare cases something else entirely, something we don't have a category for because we've never seen it before. The AI doesn't care about our prejudices. It doesn't care about what should or shouldn't exist according to our theories. It just looks at numbers, finds patterns, flags outliers, and some of those outliers might be genuinely extraordinary. Not aliens under every rock, not wild speculation about ancient probes, but real physical objects that don't behave the way our models predict and deserve serious investigation. 3I-ATLAS could be the Rosetta Stone that forces us to take this seriously. It's the high-profile case, the one everyone's watching, the one that's weird enough to demand explanation, and public enough that it can't be quietly dismissed. It has the anti-tale that doesn't make sense. It has the non-gravitational acceleration that scales too cleanly. It has the reflectivity paradox and the swarm hypothesis, and all the controversy that comes with Avi Loeb's involvement. It's a circus, in some ways, but it's a useful circus. It focuses attention. It makes people ask questions they wouldn't otherwise ask. But if we're smart, we'll use it as a catalyst to re-examine everything else we've observed, to mine the archives, to look for patterns we missed, to apply these AI techniques not just to the flashy cases, but to the entire population of small bodies we've catalogued over the past century. Because if 3I-ATLAS isn't unique, if it's one example in a broader population of strange objects, then the universe is trying to tell us something, and we've been ignoring it for 30 years. The challenge is resources. Following up on anomalies is expensive. Telescope time is precious, allocated years in advance, fought over by competing proposals. You can't just point a major observatory at every weird object and algorithm flags. You need to prioritize. You need to make choices about which anomalies are worth investigating and which are probably just noise. And those choices will be guided by the same theoretical frameworks and cultural biases that caused us to miss these objects in the first place. But maybe that's changing. Maybe 3I-ATLAS is forcing a cultural shift, making it acceptable to propose bold hypotheses, to allocate resources for high-risk observations, to take dynamical anomalies as seriously as visual ones. Maybe the next generation of astronomers, the ones training right now, will grow up in a world where interstellar visitors are expected, where anomalies are opportunities rather than embarrassments, where the goal isn't to fit everything into existing categories, but to discover new ones. Because if 3I-ATLAS isn't unique, if it's one example in a broader population of strange objects, then the universe is trying to tell us something, and we've been ignoring it for 30 years. The data was there, the residuals were there, the objects were there, sitting in our catalogues waiting for someone to notice. The AI noticed. Now it's up to us to follow through, to do the hard work of characterizing these anomalies, understanding what they are, and figuring out what they mean for our understanding of the solar system and the galaxy beyond. Maybe most of them will turn out to be mundane, measurement errors, peculiar outgassing, unusual compositions that fit within known physics once we look more carefully. But maybe one or two will be genuinely strange, and those one or two could teach us more than all the ordinary objects we've studied so far. That's the promise and the terror of AI-driven discovery. It finds patterns we can't see, asks questions we didn't think to ask, and forces us to confront the possibility that reality is more complicated than our theories suggest. 3I-ATLAS might be the first, but it won't be the last. The anomalies are out there. We just have to be brave enough to look for them. Part 14. The Exoplanet Surprise of 2025. Rogue Planets with Dust Halos. A cosmic echo of 3I-ATLAS. Something strange happened in the exoplanet data this year, and almost nobody noticed at first. Astronomers were conducting routine transit surveys, watching distant stars for the telltale dimming that reveals planets crossing in front of them. The method is simple, reliable, and has discovered thousands of worlds. But in 2025, a handful of observations started showing up that didn't make sense. The light curves weren't clean. They showed extended, diffuse halos around what should have been singular planetary bodies. These weren't rings like Saturn's. They weren't debris disks like the ones we see forming around young stars. They were something else entirely. One candidate in particular caught attention. The object appeared to be a rogue planet, a world ejected from its parent system and drifting alone through interstellar space. But it wasn't alone in the way astronomers expected. Infrared observations revealed a persistent cloud of material surrounding it, material that by all rights should have dispersed long ago under radiation pressure and the influence of stellar winds from nearby stars. Yet there it was, stable, coherent, and utterly inexplicable under standard models. The parallels to 3I-ATLAS are impossible to ignore. Both objects involve bodies surrounded by diffuse material that defies classical expectations. Both challenge our understanding of how tails form, how debris behaves, and what kinds of structures can remain stable over cosmic timescales. The rogue planet's halo shouldn't exist according to our textbooks, just like 3I-ATLAS's anti-tail shouldn't point at the sun. When one anomaly appears, you can dismiss it as an outlier. When two appear, separated by millions of kilometers, and entirely different contexts, you start wondering if the textbooks themselves are wrong. So what could create such a halo around a rogue planet? The leading hypotheses are violent and dramatic. Perhaps this world experienced a giant collision, an impact so catastrophic it launched millions of tons of debris into orbit. Perhaps it once had moons that were tidally disrupted, torn apart by gravitational forces and scattered into a cloud of fragments. Perhaps the planet itself is disintegrating, slowly losing material to the void as internal heat or radiation pressure tears it apart from within. Each scenario is plausible, each has precedent somewhere in our solar system or in computer simulations, but none of them fully explain why the debris would remain so coherent, so stable, over what must be millions of years of drift through interstellar space. There's another possibility, one that researchers mention quietly in conference hallways, but rarely put in papers. What if some of these halos aren't natural at all? What if they're the remnants of artificial structures, debris clouds left behind by long-dead civilizations or failed engineering projects? It sounds like science fiction, and maybe it is. But when you're staring at data that makes no sense under any natural model, you have to at least consider alternatives. The universe is old. Civilizations could have risen and fallen countless times before our sun even formed. If they built things in space, if they launched structures between the stars, some of those structures would still be out there, drifting, decaying, leaving trails of debris in their wake. The stability question is crucial. For a debris halo to persist around a rogue planet, the fragments need to remain gravitationally bound despite radiation pressure, despite collisions, despite the slow, inexorable pull of passing stars. The math is tricky but not impossible. If the fragments are large enough, if their relative velocities are low enough, if the overall mass is distributed just right, you can achieve a stable configuration. It's like a vastly scaled up version of Saturn's rings, except without a parent star to provide the constant gravitational anchor. The system has to be self-stabilizing, held together by the weak mutual gravity of countless small pieces. Now imagine that such systems aren't rare. Imagine that violent collisions in exoplanetary systems happen more often than we think, that disrupted moons and shattered worlds are common, and that the galaxy is littered with rogue planets trailing clouds of debris. Most would be too faint to detect. Most would pass through interstellar space unseen, dark and cold and invisible to our telescopes. But occasionally one would wander close enough to a star, close enough to our sun, and we'd catch a glimpse of it. 3I-ATLAS might be exactly that. A visitor from a violent past trailing a swarm of fragments from some long-forgotten catastrophe. The observational challenges are immense. Distant exoplanetary systems are hard enough to study when the objects are bright and compact. Diffuse halos are orders of magnitude fainter, easily lost in the glare of background stars or misattributed to instrumental noise. Our surveys are biased toward finding clean, simple objects. We're optimized to detect planets, asteroids, and comets that behave according to the rules. When something breaks those rules, when something shows up as a smudge or a halo or an extended structure, it often gets filtered out, dismissed as an artifact, or simply ignored because we don't have a category for it. But what if we've been filtering out an entire class of objects? What if the universe is full of debris systems, swarm structures, and complex multi-body configurations that we've been blind to because our telescopes and our models weren't designed to see them? 3I-ATLAS forces us to ask that question. The exoplanet halos force us to ask it again. The pattern is emerging, slowly, reluctantly, like a picture coming into focus through fog. There's a broader implication here, one that extends beyond individual objects. If exoplanetary systems routinely produce long-lived debris clouds, if collisions and disruptions scatter material across interstellar space, then the galaxy is messier than we imagined. It's not just stars and planets and clean Keplerian orbits. It's full of ghost clouds, rubble fields, and structures that don't fit our taxonomy. Some of those structures will be ejected into interstellar space, flung out by gravitational interactions or stellar encounters, and they'll wander for millions of years until they happen to pass another star, our star. And when they do, we might see them as comets, or asteroids, or mysterious visitors that defy explanation. 3I-ATLAS might not be unique. It might not even be unusual. It might just be the first time we looked closely enough, with sensitive enough instruments, and caught one of these wanderers in the act of crossing our solar system. If that's true, if the galaxy is full of such objects, then we're standing at the edge of a vast population we've never systematically studied. Every interstellar visitor we detect might be carrying clues about distant systems, ancient collisions, and processes we've never witnessed firsthand. So here's the question that should keep you awake at night. If space is littered with ghost clouds and debris halos, if rogue planets and shattered moons and disintegrated asteroids are drifting between the stars, how many have already passed through our solar system undetected? How many are out there right now, too faint or too dark or too diffuse for our surveys to find? And what happens when we finally develop the technology to see them all? When we turn on instruments sensitive enough to map every piece of debris, every fragment, every strange structure drifting through the void? Because if 3I-ATLAS is part of a galactic ecosystem of debris, if it's just one member of a vast unseen population, then the universe is about to get a lot more crowded and a lot more interesting. Part 15. The Big Picture. The year multiple disciplines broke their models. 2025 might go down in history as the year the model started cracking, not breaking entirely, not shattering into irreparable pieces, but cracking, developing fissures, showing stress lines that suggest something fundamental is shifting in how we understand the cosmos. 3I-ATLAS is one crack, the exoplanet debris halos are another, the solar sail experiments, the artificial intelligence discoveries in old comet data, the James Webb Space Telescope findings on small body reflectivity. Each one, taken alone, could be explained away. Each one could be dismissed as an outlier, a measurement error, a quirk of observation. But when you line them all up, when you see them emerging across multiple, independent disciplines within months of each other, you start to wonder if the universe is trying to tell us something. Science thrives on anomalies. It needs them. Every major breakthrough in physics began with an observation that didn't fit the prevailing theory. The precession of Mercury's orbit that led to general relativity. The black-body radiation problem that birthed quantum mechanics. The accelerating expansion of the universe that forced us to invent dark energy. Anomalies aren't mistakes. They're doors. And right now, in late 2025, we're standing in front of several doors simultaneously, trying to decide which ones to push open. 3I-ATLAS is the most dramatic of them. The one that captures public imagination. The one that lets people like Avi Loeb propose wild hypotheses about swarms and artificial structures. But it's not alone. The discipline of small-body astronomy is experiencing a quiet revolution, a shift in perspective that's been building for years and is finally reaching critical mass. We thought we understood comets. We thought we understood asteroids. We thought we had a taxonomy, a classification system that cleanly divided solar system objects into categories. But 3I-ATLAS doesn't fit. 1I Oumuamua didn't fit. 2I Borisov mostly fit, but even it had oddities that made people uncomfortable. The pattern suggests our categories are too narrow. We built our understanding of small bodies based on what we could see, what we could detect with 20th century telescopes and surveys. We studied the brightest objects, the ones with obvious tails, the ones that behaved predictably. We built theories around them, but selection bias is a harsh mistress. If you only study the objects you can easily see, you'll never know about the ones hiding just below your detection threshold. And there might be a lot of them down there, a whole population of dark movers and diffuse structures and objects that don't emit dust tails or outgas volatiles in ways we recognise. The human response to these anomalies has been predictable and fascinating in equal measure. Resistance first, scepticism, appeals to conservative explanations, to models that require minimal adjustment to existing theory. This is healthy. Science should default to the simplest explanation that fits the data. But there's a line between healthy skepticism and reflexive dismissal, and that line gets harder to see when your entire career has been built on a particular theoretical framework. When someone suggests 3I-ATLAS might be a swarm, or that it might have artificial components, or that it represents a class of objects we've never categorized, the response from mainstream scientists is often swift and negative. Not because the ideas are proven wrong, but because they're uncomfortable. They require rethinking too much, discarding too many assumptions, admitting that decades of careful work might have missed something fundamental. But there's another response, quieter but growing. Curiosity, open-mindedness, a willingness by some researchers to say, "We don't know," and mean it, to propose bold hypotheses and design observations that could test them. This is where progress happens, not in the loud debates on social media or in the dismissive comment sections of press releases, but in the quiet work of designing better instruments, writing better detection algorithms, and allocating telescope time to follow up on the weirdest, most anomalous objects. So what happens next? If 3I-ATLAS truly is part of a larger pattern, if it's not a singular freak but a member of a hidden population, then we need better tools. We need surveys that can detect faint, diffuse objects. We need machine learning algorithms that can scan archival data for subtle orbital anomalies. We need multi-wavelength observations that can characterize composition beyond what optical telescopes reveal. We need polarimetry, radar, infrared spectroscopy, and high-resolution imaging campaigns that track how these objects change over time. We need, in short, a systematic effort to find and study the objects that don't fit our models, rather than just cataloguing the ones that do. The potential payoffs are enormous. Discovering new classes of interstellar objects would revolutionize our understanding of how planetary systems form, evolve, and eject material into the galaxy. Learning about Exoplanetary debris fields and collision processes would give us insight into environments we can never directly visit. Uncovering natural phenomena we don't yet understand might lead to new physics, new chemistry, new insights into how matter behaves under extreme conditions. And yes, there's the outside chance, the speculative possibility that gets dismissed and mocked, but never quite goes away, that we might find evidence of artificial structures, relics of other civilizations, probes, debris from engineering projects. It's unlikely, it's extraordinary. But extraordinary claims require extraordinary investigation, not extraordinary dismissal. There's an ethical dimension here too, one that rarely gets discussed in academic papers but matters enormously. What happens if we do find something artificial? What happens if the first confirmed non-natural interstellar object crosses our path? How do we verify it? Who decides what it means? How do we communicate that finding to the public without causing panic or wild speculation? Are we ready, as a scientific community and as a species, to deal with that possibility? The answer, honestly, is probably no. We're not ready. We haven't even agreed on protocols for how to announce such a discovery, let alone how to respond to it. But maybe we don't need to be ready. Maybe the universe doesn't care about our protocols and our comfort levels. Maybe it's going to keep throwing anomalies at us until we stop trying to fit them into boxes and start building new frameworks that can accommodate the full spectrum of reality. 3I-ATLAS is one lesson in that curriculum. The exoplanet halos are another. The next anomaly is probably already in someone's data, waiting to be noticed, waiting to crack another model. Here's the vision. A new era of small body science, one that blends classical astrophysics with materials science, artificial intelligence, and open theoretical speculation. An era where we don't just catalogue objects but try to understand the full diversity of what's out there. An era where detecting something weird isn't a problem to be solved but an opportunity to learn something genuinely new. 3I-ATLAS might just be the opening chapter of that story. Because history shows us something important. When reality breaks the rules, we don't discard it. We don't file it away under unexplained and move on. We investigate, we push, we build better instruments and ask better questions and refuse to accept that nature should conform to our expectations. That's how science advances, not through confirmation of existing theories, but through the uncomfortable friction of data that doesn't quite fit. So what else is out there, waiting to rewrite what we think we know? What other visitors are drifting through the solar system right now, too faint or too strange for us to notice? What other anomalies are sitting in our data archives, dismissed as noise, filtered out by algorithms that weren't designed to look for the impossible? We won't know until we look. We won't find them until we're willing to accept that the universe might be weirder, messier, and more interesting than our textbooks suggest. 3I-ATLAS isn't the end of a mystery. It's the beginning of a question, and the answer, whatever it turns out to be, is going to be worth the wait.